my talk from a Lambda-Lith to an event-driven architecture, let's take a look what we are actually talking about, right? So first I'm giving you a little of introduction. Also Danny did that already. And then we are going to explore, okay, what is actually Lambda-Lith, right? Maybe all of you know it or not, but we're first going to introduce that term, what it is actually, and then we are going to reflect on how can we maybe do a little bit better. So to be honest, this is more like the journey we at Siemens did like the 3 past years. So where we started building our systems and how we build them today. And to showcase that, I then brought three different projects, and of course, in the end, we're going to wrap it up. So who am I? I'm Leo. Danny said it all, solutions architect here with Siemens, involved with AWS, and mostly into serverless stuff. So that's also why we are going to talk today about mostly serverless architectures. And when it comes to an architecture, as a solutions architect, we always aim for the best solution, right, or an optimal way. It's like it's supposed to cost nothing, it's supposed to scale high, right? And back then, this is what our architecture looked like. So this is when you get started with AWS, when you get started with serverless architectures, this is probably what you first is going to see when you get started, right? We have an Amazon API gateway, AWS Lambda, and Amazon DynamoDB, and they are great, right? Serverless services and all good, but there's no Lambda-Lith yet, or what is a Lambda-Lith? So to discover the Lambda-Lith, we actually have to zoom in a bit in the Lambda function. And what we would do, or the Lambda-Lith is more like a word combination of Lambda, because AWS Lambda is our compute platform, and a monolith, because we are building monoliths. And we would do something like this. So we have our favorite Node.js framework, in our case Nest.js, and there you just define your REST API, right? So your routes, in this case, we have a post route for like orders, we want to create new orders, and then you do all your stuff in code. So that's like how we traditionally build servers, and it's all good, but this time we say, okay, we don't want to deploy it on premise, we just put it in the Lambda function, and there you get the Lambda-Lith. And with each of those solutions, there are trade-offs, right? So with the Lambda-Lith, there's advantages. So when you're talking about AWS Lambda, you soon get to experience like cold starts. And that is because on an initial invocation, AWS actually has to download your source code files before it's able to execute it. And that time is referred to as a cold start. But then every subsequent invocation of the same Lambda function, you don't have that cold start anymore because the source code files are already there, right? And of course, it's easy to get started because maybe you already built that server for an on-premise use case, and now you want to leverage all the advantages of the cloud. So with very little, let's say, glue code, you can actually manage to migrate your existing applications to the cloud. But of course, every solution ships with advantages and disadvantages. And some disadvantages are that even though you have less cold starts, because it's all in a single Lambda function, your cold starts tend to take longer. Why is that? You're bundling all in one bundle, right? That bundle is bigger because everything is in there. Therefore, it takes longer. And with this type of architecture, right, we have a REST API, we have the Lambda function and our database. We only have synchronous invocation. Of course, that's sufficient for many use cases, and there's nothing wrong with that at all. But of course, as things grow, right, those projects we're building, those applications, they're evolving. We see new requirements coming in over and over again. It might be the limit. And in the case of AWS Lambda, you actually have a hard limit you cannot avoid. That means like your bundle size you're uploading is a maximum of 50 megabytes zipped and 250 megabytes unzipped. So if you hit that limit, you're really in trouble and you need to re-architect your solutions to somehow circumvent that. And of course, the big monolith disadvantage, you have a single bottleneck. So even you're using AWS, you're scaling, you have tremendous scaling capabilities, but if you introduce a bug that avoids your server to start, it will break that Lambda function, it will break your application. But with that in mind, we can already, we have one more thing, like there's actually an own AWS has its own take on the Lambda-Lith, so that's nothing I came up with. And when we zoom in on the very top left, we actually see it's an anti-pattern. So that raises the question, okay, are we now like doing everything wrong? Is it, or are we supposed to do better? And like one quote on the very bottom I really like, because I felt when I read that really much related, it definitely increases the cognitive burden for developers. At least that was the case for us. Because if you go back to the Lambda-Lith itself, if you imagine this, right, we have here the product service, we don't have any error handling, right? So what is supposed to happen if we fail to create an order? Are we rolling back? We should like unreserve the product again. All those things are not handled. And now if you imagine those 4 lines of codes with tremendous try-catch blocks, that's what causes the cognitive burden. And with that, we successfully introduced like the Lambda-Lith. And as we will do with the Lambda-Lith and all subsequent projects I'm going to bring with you today, we are going to think about, okay, why have we used it in the first place, and what have we learned by applying those? And in our case, we used it because we just did not know any better. Like 3 years ago, that was mostly like the start of our cloud journey. We had them deployed as like very fast, and it worked. It scales, it works, and you're happy. But again, you have those trade-offs. You have to have those trade-offs in mind. And again, like the replatforming case, if you have already a REST server running somewhere, it's an easy way to migrate to the cloud. But what have we learned? Well, the whole cold start thingy, right? So you want to know the implication it ships with, so it's a trade-off. Do I want to have like multiple faster cold starts, or do I accept, or do I want only one cold start, or like less cold starts, but I accept that a single cold start might take longer to spin up? And of course, what we just said, it's like a cognitive burden, or can become a cognitive burden. Of course, not all monoliths are referring to all monoliths, but speaking how it was for us, and we had like that single bottleneck, and that's of course something to avoid. And that actually brings us to our first project I want to share with you today, and we called it Coin. And the scope of that Coin project is to actually inform fellow Siemens employees about their stock options and like equity plans they're eligible. And once a year, as a Siemens employee, you can subscribe for one of those plans, and then you're fine, right? So it's mostly informational, web app, but also then you're allocating like your options through that web app. And we want to learn, right? So we learned Lambda-Lith, it's okay, but maybe we can do a little bit better. So let's take a look how we built it. And that looks very similar what we already got, right? So we only swapped out like the DynamoDB, like the NoSQL database of Amazon, with an Aurora instance. Like Aurora is like the relational database, comes in different flavors. We used PostgreSQL, but to actually get the difference, we have to zoom in, because now we would again have like an API gateway endpoint, a Lambda function, reader and writer instance from the Aurora, but we would have multiple instances of those, right? And we would start calling them microservices. So now we have an absolutely fine architecture, right? So we eliminated our single bottleneck, the Lambda function, and we deploy it to production on a Friday and go home and are satisfied, right? So that's what we do. But turns out, on the Monday, you go back to office, and then you realize, oh, wait a second, we actually not only have a few clients, like HR is actually on an annual basis running email campaigns, informing all 300,000 eligible Siemens employees, hey, dear Siemens employees, now please go to coin and allocate your stock options. So what's going to happen? We are having a lot of clients causing a lot of traffic on our API gateways, so that's fine, right? We're using serverless technologies. That's why we use them in first place, because we are expecting that peaky workload. So API gateway, I think it has a quota about 10,000 requests a second, so that's okay. Our Lambda function also, right? They spin up multiple instances, that's okay. But each Lambda function, which spins up, right, on invocation to serve the high amount of requests, is attempting to connect to the database. And we still have a single writer and a single reader. So of course, what's going to happen, we are trying to open multiple connections, and we will just overload the database and we fail to serve our requests. So what we accomplished, we got rid of our compute bottleneck, but we successfully introduced a database bottleneck. So how can we circumvent that? So first thing you actually want to do is you want to use a so-called like RDS proxy. And that thing, what it's meant for is, it is actually taking care of those multiple connections. So this component allows, is in the end a connection pool, or the AWS solution for connection pooling for your database instances. But still, we had many requests, right? It was a very read-heavy application. We then could also swap out like a single reader and introduce a so-called Aurora autoscaling group. Autoscaling, yeah. And what it does is it lets you track a certain metric, for instance, database CPU load, and then based on that metric, add additional readers to your database cluster. And with that, we eventually managed to serve all requests and survive the annual Siemens email campaign, and all Siemens employees got happy that they could allocate their options. So that's for the first application. Give me just a second. So again, why would you use it? It's again the replatforming thing, right? We still have like smaller Lambda-Liths, but still somewhat the same. We still only have synchronous execution, and we already managed to decouple parts on the compute side, right? But what have we learned? Don't use a single bottleneck as a database. Obvious, it sounds stupid, like when I'm talking about that, it sounds obvious, but it was not obvious back then. And it's again, with the small Lambda-Liths, it's the same thing. You have the trade-off, the cold starts. You should be aware of, I would not say it's a problem, but you should know the implications that it ships with, and of course with the database. Single database is a bottleneck, but if you have that, and if it's in an AWS Aurora, make sure you want to use an RDS proxy if you have multiple connections, and if that's not sufficient, introduce like the auto scaling. So that's why we go to the cloud provider in the first place, right? Because we want them to do the scaling for us. And that actually leads us to the second project I want to share with you. Like after we eventually managed to deliver coin, we got a new project, and it's called DVM, like it's the Digital Visit Management, the abbreviation for that. And what you do with that, as within Siemens, right, we have like a lot of business partners. We want to get involved, we want to get in touch, we want to do business, and we want to invite them because we want to show what is Siemens capable of doing, right? So we have new facilities, new factories like Industry 4.0, like we have those showcases. And for instance, I want to say, okay, let's invite the whole InfoQ attendees to a Siemens site, and then I'm going to show you what we can all do. And this tool allows me to plan that. So I can schedule meetings, I can schedule tours through our factories, you get QR codes so that you get through the gates. So as you can imagine, I should not be I should not be capable to just schedule a meeting or such a tour for, I don't know, 100 people. There should be an approval process, right? So probably my manager wants to know what Leo is planning on this event, on this conference. And so this is a lot of approval, a lot of states, a lot of management needed. And that's actually a screenshot of a first version of a state machine we had for all those approvals. And you can even imagine like one of those small boxes even unfolds in its own state machine. So it's a lot to consider, right? You have different factories, different interfaces all over the place, and you somehow want to manage it, right? So we need to build an approval workflow. And the good thing, AWS got us covered when it comes to approval workflows, namely AWS step functions. Step functions is like I refer to it as the workflow engine that AWS provides for us. So what you can do is you can define a workflow. So in this example, we have like the start and the end, right? And we have like a single action. We want to emit an event to Amazon Event Bridge, so the event bus. And usually when you just normally invoke such a step function, it does all the steps you're defining, right? Writing something to the database, an additional API call, putting an event to Event Bridge, and in the end it will succeed and like the execution is done. However, there's like this wait for callback mechanism I want to introduce you a bit more in depth, because with that enabled, if we think about having like an event, we can link that step function to an event bus. So whenever an event occurs, that step function starts, right? And now usually we emit the event again on the event bus and we end. However, with that wait for callback mechanism, we actually emit still that event, but we pause the step function. So we don't finish the step function just yet, we pause it, and that event that was emitted, that includes a token. And now we're waiting, right? But what you will usually do is you subscribe another listener, in this case a Lambda function, to that event, including the token, and now you want to have that Lambda function to save the token to a database. Because now we're waiting, right? We're waiting for an approval. I don't know, is Leo allowed to invite all the people to the next Siemens site? Yes or no, we don't know. And of course, like, you know, when have you asked your manager the last time for an approval? Maybe for vacation, to come here to this conference, right? It can take some time, right? So the good thing about this type of workflow is while you're waiting for the approval, you actually are built like almost nothing as infrastructure costs. The only thing you're built for is a little bit of storage, right? Because you store the token within a database, but you have no compute costs because the step function is paused. Event Bridge is like the serverless event bus, so if there are no events, no costs. Same goes for the Lambda function. But then, when you're approved, right? When I'm approved to show you the next Siemens site, we again have an event on the event bus, Lambda function listening to that, reading the token from the database, and then finally submitting the token back to the step functions API. And just now, once that approval was granted, the step function would continue, and in this case, it finishes. But of course, now you could do everything else, right? Any subsequent things, like sending out emails for confirmation of the approval, those would be the usual subsequent steps you want to do. And with that in mind, we actually can take a look how we built our architecture. So we again, right, we want to do like microservices. Now we have learned, right, don't use a single bottleneck, don't use the database as a single bottleneck. So now we moved databases to each microservice. So each microservice has its own database. And also microservice, just to visualize that it's not only a Lambda function API gateway, it can have multiple components like queues, additional listeners, so on and so forth. And then of course we have Event Bridge for our choreography. So now we can actually communicate in an asynchronous fashion, right? And then the counterpart orchestration, we're using step functions for that. And in our case, we put that step function in a scope we called like the orchestration service, but we'll see how that turned out. And now again, we can think of why have we used it, right? Why did we choose such a type of architecture? So first of all, asynchronous communication, right? So everything is asynchronous, so we want to also be able to implement those requirements. And also for us, like this whole event-driven mindset was also closer aligned how we actually think or how we would receive the requirements. Because it usually was, okay, when a booking was approved, please send out an email to the following stakeholders. When the catering is scheduled, then we need to feed that back to some other channel, right? So it's actually always, those requirements naturally were like defined with like, okay, when something happens, please do something else. And for us, it turned out that was actually quite nice and aligned with this event-driven approach. We more like managed to decouple our systems, right? So if a microservice now fails, only that single feature or microservice failed and not our whole application. So that's a huge benefit, of course, and the whole step function to implement the orchestration, also a huge benefit to do so. Like, what have we learned? We need to plan for observability because now suddenly we have dozens of microservices, dozens of Lambda functions, listening and step functions and other pieces and components asynchronously somehow interacting with each other, and we want to keep track what's going on, right? So that's like a big lesson because maybe you're submitting some event to some microservice over here, but some subsequent microservice horribly fails, and you want to know that actually that event caused like the downstream failure. So that's a big thing, big lesson learned we had, because in the end, like it blew up, and then we were like, okay, we have no idea why. So you want to actually trace what's going on in your system. And it's again, one big step function we introduced, right? We have this orchestration service. It's not a good thing. Like similar how the initial Lambda monolith was like an okay-ish idea. We want to break things up. We want to put them in different scopes. And also it was hard for us from a mental model because we are in this application, we are orchestrating not only bookings, we are orchestration factory, onboarding users, onboarding, and many things. And then we were like, okay, where should we put that piece? We are doing orchestration, so it should go in this orchestration service, right? But actually, it's heavily related to a user, right? So maybe it should go in the scope of a user service. So that's what I would not do that again, like creating its own orchestration service, because that at some point did not align well with our mental model. And the last one is actually a tricky one. Within AWS, especially with this serverless event processing solutions, let's call it that way, like namely Event Bridge, like the event bus, but also SQS, where we can queue different events and process them. They all have a so-called delivery policy. And when you look it up for certain services, the delivery policy for most services is at least once. So that does mean not 0 times, mostly 1 time, but it can be also 2 times. And if you remember, like what I showed when I walked you through the step function part, right? That was triggered by an event emitted by the event bus. And now what happens if we have 2 events, 2 step functions start, trying to do the same thing? Like that's caused side effects you cannot imagine, or it's like a huge, it's like hard to describe, it's hard to grasp, but it's a mess, let's put it this way. Like you don't want to debug those kind of side effects. And we maybe see with the final and last architecture how you can actually deal with duplicated events. And that leads us to the last architecture I brought with me today. It's called MDLA, an abbreviation for My Digital Lab Assistant. We built that for our Siemens Healthineers colleagues. And what problem are we trying to solve? It's in the end, it's a customer portal. So if you're a customer of Siemens Healthineers, you buy your favorite medical device, but then of course, different things can fail. It does not get shipped, it's damaged, it has the wrong color, I don't know, and it's broken whatsoever. And in that case, you usually contact your Healthineers contact, but to somehow streamline this in a more structured manner, we built like MDLA. And when I said like those duplicated events can become a mess, there's actually a concept that allows us to take care of that. And that's namely idempotency. And the definition I've looked up here is that idempotency is like the capacity of an application to identify repeated events, prevent a duplicate, inconsistent, or lost data. Clear, right? Next slide. Let me rephrase that. We learned those duplicate events, they can happen, right? That's not good. But we want to know when they arise, and then we want to treat them properly and handle them. And that's what idempotency is about. So I've brought an example, right? So let's say we have a Lambda function, and we're trying to insert a new record, a new row within our database. So now, when we have duplicated events, we would insert 2 records. So that's obviously not a good thing. So what you now do, instead of directly inserting that event, you want to somehow identify that event, right? So either you have like your own ID that uniquely identifies an event, or you could think of like hashing the whole event to get a unique identifier. And then before you put it in the database, you actually want to look up that event ID in a so-called control table. So in this case, could be some cheap DynamoDB table. And then you have 2 cases, right? Either the event does not exist in the control database, so we know, okay, we have not processed that event already, so we are safe to put it in the original database, and then finally also have to update the control table. And the other case, right, so we already have processed an event, so we get a hit in our control database, and then we know, okay, we already processed that event, so what should we do? Most of the time, you don't want to do anything. You just drop that event, and because you know you already did that. And with that in mind, we can actually take a look how we build MDLA. So lessons learned, right? We don't want to do its own orchestration service. Therefore, we put like step functions in each microservice where needed. We would again have like multiple microservices. So microservices are allowed to communicate with each other, right? So we usually would have client credentials for each microservice. So we have an authorization in place. Again, have like an event bridge, but for asynchronous communication. But what I did not mention actually is it's fairly tedious for clients to connect to all of our microservices, right? So we have dozens or even hundreds of microservices, and we don't want the clients to connect to each microservice, right? Aggregate data across microservices, that's very tedious. So instead, what we introduced in this project is so-called gateway service. It's again an API gateway and a Lambda function, and we would this time deploy it in a private subnets, and that's why because then we can create so-called interface endpoints and assign those downstream microservices so-called resource policies. And with that, we switched like this client credentials overflow exchanged it with AWS IAM. So the AWS authorization service, so to say. And that, of course, right, that's why we choose the cloud provider. We want to pass on like the responsibility, right? So because we don't want to keep track of our secrets and so on and so forth. So that's why we chose to implement it in this way. And with that, we actually unveiled the last architecture. But again, why did we choose it? All the previous benefits, right? So we entered like this rabbit hole of event-driven architectures. So of course, all those advantages apply. And in this case, we really benefited from those private API gateways because we switched out like our custom authorization mechanism and leveraged like what AWS already provides for us. And of course, the whole client connections with the gateway service. But lessons learned, I cannot stress it out enough. It's again, observability. You want to start tracing, like X-Ray is the AWS service to do so, but you of course can also use open telemetry, I think it's called. And again, those private APIs, this was kind of both like a benefit why you wanted to use it, but to be honest, we discovered it on the way. So it was also a lesson learned for us. And with the step functions, that's actually an interesting one because you can actually version your step functions and assign different aliases for them. And that's actually a very neat feature because that allows you to publish new versions, new adapted workflows without breaking anything old, right? So that ensures you some backward compatibility. Because imagine you have like your approval workflow, it's running, right? You're waiting for approval, but now you're changing the overall process. You're deploying a new step function, and like, how would you do that, right? So you have to still wait until like the old workflows succeeded. So with that, you can actually have like run multiple versions of your step function simultaneously. And with that, we can actually wrap it up. So we started with a very simple architecture, like the serverless architecture when it comes to AWS with an API gateway, a similar Lambda function where we have all our code inside and a database. We switched it up, right? We changed that bottleneck, that compute bottleneck in favor of a database bottleneck. Then we discovered like step functions to actually implement approval workflows, which then allowed us to implement a more complex system with a lot of orchestration going on, such as like the digital visit management. And then with the final architecture with MDLA, we implemented our handlers in an idempotent way. So we are checking have we processed an event already or not. And with that, we eventually built more resilient architectures. And that was more like the journey we've taken. And I'm looking forward for your questions. Thank you. Well, like one question I have, or please use like the InfoQ app and let me know what you think about the talk. A lot of green smileys. No, just let me know. Really appreciate it if you take some minutes to give me some feedback.
Hi, Leo. Thanks so much for a great talk. I had a question about your last, the best of the best architecture that you built. Can you go back in the slides?
Sure.
This one. So you introduced the Lambda function that is going to be taking in all the requests coming from the users. So did you make your architecture synchronous in the end of the day? So is your Lambda function waiting on the process to complete?
You mean the very first one?
Yes, that very first part.
Yes.
And a consequent question, is this your new bottleneck?
Yes, it is. A very good question. Yes, it is. Yes, and we are things we are elaborating right now is to use, first of all, why did we do that, right? We learned that already, single lambda bottleneck, it's a bad thing. We want to avoid that. In this case, we are not doing the heavy business logic in there. We are aggregating across multiple services. So of course, there's the risk to have that single bottleneck, but in our case, we accepted that risk because back in the time, we've been good at building small Lambda-Liths, so we built a small Lambda-Lith, obviously, right? How would it do things today? Like, there are different solutions you could tackle it, right? So one would be, for instance, or what also we are investigating is, for instance, using AppSync. Like, that's the GraphQL, like the managed allows you to build GraphQL APIs, and it's also fully serverless service managed by AWS, right? And then you would get rid of your bottleneck. But that, obviously, yes, very good catch. Again, a bottleneck. But in this case, we accepted that risk. It's an intended bottleneck.
Yeah, thanks.
One question more towards the application side, like one issue that I always found with the serverless architectures is the unit testing, because the whole application is interdependent on calling both a tree, and then to properly test it, you need to have it cloud. So how did you solve the unit testing issues?
I don't know whether I fully understand your question, but like all the application layers, like all our controllers, all our Lambda function code, we would unit test. So, yeah.
For example, Lambda is going to call event bridge, or is going to call, do you have like some mocks for that?
Yeah. So best case scenario, I would love to say that we are doing it all in a fully automated way, and we build up whole test environments within our CI/CD environment, do our end-to-end test, and then tear it all down. But maybe at some point, but we don't do that right now. What we do instead is, at least locally, we use local stack. So that's like a framework or a tooling that allows you to emulate some AWS environment, and then you can at least locally, start your AWS services. Within our CI/CD integration, we run unit tests, we do linting, and we do some integration tests where we mock like databases. Because like for DynamoDB, there exists a Docker image, of course, also for PostgreSQL and those relational databases. So we spin those up. But yes, like Event Bridge or like those other managed or proprietary AWS service, we just mock them away in our tests. So there's a not full end-to-end test, but at least from the application layer to the database layer.
Thanks.
So we don't use AWS in our case, but generally we have huge volume APIs that are going to the database for data, and normally this data is they are very large. So we queue the request to the database. But what if the containers receive the request and they are willing to accept the request? But then when the data is processed in the database, these results are coming back to the container, and then the container basically is having problem. And there is no probably queuing. There is a queuing mechanism when the requests go to the database. But what if the reverse queuing? Is there a way to queue also the response that comes from the database?
I'm not sure whether I fully understood the question, but you're asking whether we can queue, like we're sending a request to the database, and you're asking whether we can queue or save the response.
Yeah.
Definitely there is a way to do that. You had to build it, right? So when you, from your Lambda function, or from your compute environment, you send the request to the database, you get a result, and then you just can save that result somewhere. So I don't see anything that would like restrict you from doing so, but I have to admit I don't fully understand like the use case or.
Yeah, thanks. Maybe we can take it.
Sure, we can discuss it offline.
Let's say you have a big monolith and you want to split it up. How small should a small piece be? Should it be just one REST endpoint or one entire domain? And
a very good question. We asked that question ourselves a lot because we have a lot of monoliths we're trying to refactor. And the unsatisfying answer is, of course, it depends. Like, there is no like hard rule that you say, okay, if your Lambda function code bundle size exceeds a certain threshold, you're doing it wrong. However, there are like methods like domain-driven design and stuff like that that allow you to define the scope or what are suitable scopes of your microservices, and then you will like naturally see, okay, where to put which part. So there are methods to build or to get started with those event-driven architectures.
Next question, if you have a Lambda which only contains of one REST endpoint, do you really then still use like an entire REST framework like Flask, and doesn't that create
Obviously you don't need that.
overhead?
You don't need that. And that also like the question we had in the beginning, right? We have again a Lambda-Lith and having like that single point of failure. What you also can do is to have a single Lambda function for all your REST endpoints. So your, I don't know, get orders endpoint invokes a dedicated Lambda function, but also like your post orders endpoint invokes another Lambda function. So with that, you would also eliminate that bottleneck.
Across your three different versions of application, you're always stuck with Lambda functions. Have you ever evaluated going for something like Kubernetes? At least the very beginning, you had this one fat Lambda, and then with Kubernetes, you could have run that apart with auto scaling. You get similar functionality. Why did you stick with Lambda?
Because we have absolutely no idea of Kubernetes, to be honest. Simple as that. So we do like, when we have like, Lambda also has its limits, right? So certain payload limits you can pass through. When we would hit those limits, of course we need, either we can refactor our application so that it fits, or we would then opt in for a provision solution such as AWS ECS, like that's the container service. So then we would go like more into this image-based. But Kubernetes, to be honest, was never an option for us.
Hi, my question is about your second project. You mentioned like having multiply microservices and those microservices having their databases, right? Should we, in this kind of solution, should we measure infrastructural costs with the benefits of this kind of architecture? And the second question related to this topic is, should the data be written synchronously to those databases?
Like to answer your first question, like whether having like a single database over multiple ones, yes, definitely that's going to cost that's going to increase your bill. But there it's a trade-off. You can also build such a microservice environment with having a single database. But then again, it's up to you whether you are accepting that risk to have that single bottleneck, to have that single point of failure. So as we did with this architecture, right? Now we also have that single bottleneck, but we accept the risk. It's more about awareness and making conscious decisions. Like there is, when I talked in the beginning, like the optimal architecture, right? So with all your questions, right, that's not the optimal architecture. So that's what we consider good, like an optimal in a local optimum, right? There's no global optimal solution for that. So it's always a decision you have to take. And you might want to repeat your second question, I have forgotten about.
The second question was about writing data to those databases. Should this be synchronous or should you just know where you wrote the specific data and while reading, extract data from that specific database?
So again, like there's no global like recommendation or like general recommendation. Like if you, for instance, rely on transactions when you're writing, then of course you want to do that in a synchronous fashion, right? But if you, I don't know, some inserts taking ages, right? And then why don't offload that to a downstream process? So again, I'm sorry, it depends.
Thank you.
Hello. You said that the Lambda processes an event at least once. In case that your Lambda have multiple transactions, then do you need to implement a rollback mechanism outside of the Lambda, or how would you advise to manage?
So you're asking where to handle those duplicated events, whether we want to do this in the Lambda or before. I would say, or personally, I would recommend to build all your handlers in a resilient and idempotent way, because you never know, right? So generally speaking, you want to protect your system, let's call it that, right? If you would consider this whole AWS cloud as your system, you only want correct data enter your system, but there's event, there are the services, right? So you cannot avoid it. And just to be sure, and there's also tooling how you can implement that in an idempotent way. So in case of AWS or with Lambda functions, you can use the Lambda Power tools, and this is a very lightweight package which does it all for you. You only have to pass in your control table, and then it's like a small wrapper, and then you're kind of safe. So there's tooling out there. Generally speaking, I'd recommend to build it all in an idempotent way, because it's just more resilient. And it's very little overhead to implement it.
Then I have another one. So in terms of migration of existing systems to serverless architectures, there is any way to migrate just part of it? Let's say you take your GraphQL and then you put API gateway in front, or you take one domain and create a Lambda function for that domain. Or how is it to migrate existing systems to a serverless architecture?
That's a very good question. We also have a lot of cases where we have to do that. So we have running on-prem applications somewhere deep down the Siemens internet, and we want to elevate them to the cloud. And of course, if you have a complex system, you cannot do it all at once. But again, you want to, and it's about you should probably have some kind of roadmap, right? Because it could be easier to migrate the whole monolith to the cloud, and then within the cloud do refactoring, try to identify domains, try to identify service boundaries, and then migrate it. But of course, also this is a step-by-step process. And what we usually would do is we would have a connection from our on-prem data center to the cloud environment. So there are different options how you can do that with probably any cloud provider. And then you just allow them to communicate, and then you can move part by part to the cloud.
Thank you.
Is there any other question? We have time for one more before we go, if somebody has one. Okay, last question.
Yeah, modeling with state machines and events can be a bit tricky. Have you any experience with how do you handle when the events come out of order?
Sorry, can you repeat that?
If the events arrive out of order, not in the intended order that you expected. Suppose you model a physical system with a state machine.
To be honest, in our use cases, we don't rely on event ordering. So we just don't have that requirement that we process all events in the same order. So that does not apply, at least for us. But what you could do, again, AWS got your back on that. There are different tools how to enforce or keep ordering of your events. For instance, using a certain type of queue, first in, first out queue, stuff like that. That way you could ensure processing all your events. And
so is the event bridge guaranteed to deliver the events in the order they were published?
I think they do best effort ordering, again, with the same thing with the at least once, right? Yeah. So if you rely on strict ordering, this might not be sufficient for your use case.
Yeah, okay, thanks.
Yeah.